We present our work SGAM, building a virtual 3D world through simultaneous generation and mapping. This is a joint work with Bei Jiuma and Shenlong Wang. In this work, we are interested in large-scale 3D scene generation. Given a single-pose RGB-D observations, we aim to produce consistent, realistic, and large-scale 3D world. 3D world generation can be applied to many applications, such as building simulation environment of surrounding traffic, urban planning for new neighborhoods, and creating virtual world in metaverse, just to name a few. For the generative 3D world, it should be able to expand to arbitrarily large scale, realistic in terms of both geometry and appearance, and consistent across different camera viewpoint and trajectories. Recently, many works start to tackle the problem of 3D generations, for example, generating human faces or simple objects. However, these works focus on addressing object-level 3D generations, and thus is not directly adaptable to scene-level generation. Another line of research tackled the problem of 3D scene generation by learning procedure of composing objects into the scene. Many methods reproduce realistic layout. However, to create realistic visual content, we still need to leverage graphic rendering pipeline and existing 3D assets designed by the domain experts. Perpetual video generation, such as Infinite Nature, can produce long video footage, but maintain only short-term consistency. These methods cannot deliver a 3D world with realistic geometry, and hence do not enforce multi-view consistency. Our solution for 3D scene generation is inspired by the pioneering work in 2D texture synthesis by Afflew and Freeman. Their proposed method iteratively grows texture by sampling patches from a given image that best fit the content in the overlap portion of the previous generated content. Specifically, at each iteration, they first grow the target image by sampling a new location to fill, then sample a patch that is realistic and consistent with the current target image. Finally, they add the new patch into the canvas and repeat the above process over and over again. At a high level, their solution is iteratively performing two operations. One is to simultaneously move a virtual orthographic camera to generate new content, and the other is to register new observation into the 2D world. Our method is essentially expanding this idea and lifting the modality from 2D to 3D. Given target scene, we grow the scene by sampling new camera pose close to the scene boundary. Since the new pose is at the boundary, the newly rendered image from the existing scene is incomplete. Thus, we exploited a generative model to complete the observations, making the resulting image realistic and consistent with the existing 3D scene. Then we integrate the newly rendered observation into the global scene, which we refer to as a mapping step. Through simultaneous generation and mapping, we gradually expand our 3D scene to infinite horizons. We will then introduce two key components in our framework. During the generative sensing step, we first use image-based rendering method to render a partial observation using the existing map. It is followed by a conditional generative stage to complete the image. Specifically, we use a simplified VQ-GAN model to conduct this task. In the mapping stage, we integrate newly generated sensor input to the current map by performing volumetric fusion. Specifically, in our work, we use the RGB-D integration in Open3D for these mapping operations, and this concludes our method. We evaluate our performance on two datasets. Caliber Infinite consists of simple 3D objects, and Google Earth Infinite consists of poses sampled from real-world 3D geometry extracted from Google Earth. Result-wise, we first present experiment result on Caliber Infinite. While other baselines suffer from mode collapse, slow decoding, and inconsistency issue, ours can produce high quality and consistent result efficiently. To increase diversity of the generative scene, we notice, besides temperature sampling, the effect of camera trajectory also play a critical part. We also conduct scene-level evaluations. First, we present a few generative scenes from different methods. SGAM generates scenes that best match with the ground truth scene distribution and have the minimum artifact caused by the view consistency. Next, we present our quantitative result on scene-level generation measured by FID, Jensen channel divergence, and the maximum mean discrepancy. While SGAM did not achieve the best FID per frame, SGAM produced a more consistent geometry across frames and best match with the ground truth distributions. Next, we present our comparison study on Google Earth. By comparison, our solution is the only one that can give realistic and consistent extrapolation towards later frames. Here are more qualitative results on Google Earth. Here are a visualization of the global mapping for 4 different scenes. Unlike any previous perpetual 3D generation method, our prediction on real-world data can produce complex and large-scale color 3D mesh. To conclude, we present SGAM, a 3D scene generation framework that produces realistic, consistent, and large-scale 3D virtual world through simultaneous generation and mappings. Our take-home message is that explicit 3D mapping helps consistency, realism, and scalability for perpetual generation. Thanks for watching, and please check our paper for details.